It's okay. Okay, thank you very much for the feedback. And today I am hoping to talk about the AGORA project to open the doors for the next 3 talks and also the weekend session that follows this workshop. So AGORA project, as you may have heard, it's a project that we are trying to compare different galaxy formation simulations in a way that guarantees the predictive power of the numerical simulations of the galaxy formation community, so that the observers can trust each other, trust us. So here, if you are a simulator, you are probably going to be using just one code, and your simulation you include your favorite physics. The other one you don't include your favorite physics, and compare those 2 simulations, and probably you want to argue that your favorite physics is really important. That's what simulators do. And to make sure that this scientific experiment is reproducible, you may want to run another simulation, a different code platform, and compare those 2 simulations in apple-to-apple comparison to make sure that the simulations are reproducible. So that's essentially the AGORA initiative, AGORA project. Sounds simple, but if we go back by 13 years, when we were slightly younger, by 13 years, you will realize that back then there was no such thing as this systematic infrastructure that allows us to compare our simulations against others. So I think one of the things that we do this week is to celebrate the achievement of Joel here. So this is the picture, the traditional picture that was taken in the Santa Cruz workshop. So after this workshop, we had the first AGORA meeting in 2012. And as you can see, Joel convinced a lot of leading developers and leaders of the community codes, like Gadget, Enzo, many codes out there. And a lot of them played a role as steering committee members of this project. So since then, 13 years have passed, and we are now a multinational, multi-institutional collaboration that had multiple workshops, hundreds of web conferences. It's not a exaggeration. We have produced so far 8 papers, and 2 more papers are in the pipeline. You may think that, comparing simulations should be easy. I mean, you have music that allows different initial conditions for different codes, same initial conditions for different codes, and we have YT that can read in any code outputs. Sounds very simple, but 13 years back, none of them existed. So essentially, YT and music and Graco, which provides the common astrophysics like cooling and chemistry, those co-evolved with AGORA in a sense that we provided the testing ground for them to test their new features, new front end for the new codes. And we also provided the feedback to them so that we can co-evolve with one another. So we started out with the dark matter only comparison in 2014, and immediately after that we started to add the baryonic physics like star formation and feedback. That was, although that was in the isolated, idealized galaxy, we were able to successfully conduct this hydrodynamics comparison. And then we moved on to the cosmological comparison. It's a zoom-in simulation. As you can see, 8 different codes at redshift 2, and then redshift 4, and then redshift 2, and some of them even proceeded down to redshift 0. So, as you can see, this process of adding one feature at a time, like co-moving coordinates, baryonic physics, dark matter only gravity, one by one, is a strategic choice for us to meticulously calibrate our codes against one another in a way that we can identify quickly what are the sources of discrepancy between the codes. So by doing so, we were able to reduce any free parameters so that we can do a systematic code comparison, not just a flavor comparison. It sounds simple, but every time you want to make this composite figure of 9 different codes, like the temperature density PDF that you can see, this is a published plot, for example. Every time you make the plot like this, the first version looks like something like this. So in between those two figures, there's like not just 5, 6 iterations, but we're talking about 70 to 80 iterations. So just going back and forth between one person and each code front. So, you know, if you start to save those intermediate, you know, epochs, then you can create a movie like this. So it's like 6 frames per second, and it's like a 9-second movie. I've shown this movie like many years ago, but I'm doing this again because it's always fun to see the reaction. But anyway, now that this infrastructure has been made, like all the common physics, common initial conditions, common analysis script, and all the infrastructures have been made public, so it's open to everybody to use. We are now moving into the science comparison. So for the past 2 years, this is a very exciting period for us. For the last 2 years, we've submitted 5 papers, 4 of them published. So, like for example, this one led by Santi Luca-Fabrega out there. He's going to be around if you have any questions. He looked at the halo and galaxy merger history, assembly histories, and removed all most of the timing discrepancies that existed between the codes. And this one sort of shows the power of this cross-platform comparison. So here you can see hydrodynamic simulations, dark matter-only simulations of 9 different codes. You can see that if you zoom in and look at the number of identified halos, systematically you can see the difference between dark matter-only simulations in a sort of dim line there. This is a satellite mass function. So hydrodynamic simulations, you can see that the hydrodynamics, including the baryonic physics, suppresses the number of satellite halos across the board when we have never calibrated our baryonic physics against the number of satellites. So we never did that, but systematically across all the codes, this happened. So missing satellite problem, gone, just by including the baryonic physics. So this satellite quenching, Ramon already talked about this. He's going to be around for today and tomorrow. Another one, Min Young, another student of mine, he's soon going to be talking about the disk morphology of the host galaxy that was formed at the center of our zoom-in simulations. So a lot of exciting science can be done now that we have, built our infrastructure. So what have we learned, and what's ahead for our collaboration? So I think this has been really a human experiment in that, it requires some willingness, the community-wise willingness to make sure that the simulations are reliable and robust, so that the observers or any people outside this tiny community, tight community of galaxy simulation people can trust us and make the simulation tool as a reliable asset when we look at any problem of the universe. So we have built this infrastructure, the public data access, all the simulation, initial conditions, and the snapshots are available. And we've written multiple journal articles, as I said, and it's 20-something to 40-something co-authors. I don't think this is a usual case for the case of simulation papers. Yet, we have not yet imploded in a way that, some may think that this theorist simulators, the egocentric people, we didn't explode. So that's one thing that we take pride in. And I believe the initial idea, the philosophy that Joel had envisioned is that this shouldn't be a one-off paper, one-off project, but as a sort of infrastructure that lasts so that the community can always have this resource of making sure that the simulations are reproducible and ensure the realism and the predictive power of our simulations. So going forward, we have had the regional workshops on top of the annual workshops that we have here at Santa Cruz. We had annual regional workshops in Asia, first one in Seoul, 2024, the second one in Osaka, 2025, just a few months back. The third one will happen in Sweden next year, May, so you're invited, you're welcome to join us. So this regional workshop was really useful for us to speed up the science papers and launch ambitious new simulations. So the weekend workshop that's going to happen tomorrow, we plan to finish up 2 more papers using the cosmological simulations that I just presented, and also launch new simulations, the high-resolution dwarf-size simulations. So just to flash some of the papers that are in the pipeline. This will be by the Thin, who gave a talk earlier this morning, but it's going to be about mergers. When merger happens, a lot of exciting, like triggering the star formation and how the star formation gets turned off. So that's going to be discussed in this paper, paper number 9. And paper number 10 is actually using a new suite of simulations, not the one that I showed you so far, but the one about the JWST counterpart, high-Z simulation, redshift 10 or above, whether the variant is physics calibrated low-Z can still reproduce the luminous objects that we see at high-Z. So these are the goal of this annual workshop, and we're also going to launch, as I said, the high-resolution dwarf-size simulations, and also lots of other projects like plane of satellites, halo morphology. So this is the point that I'm trying to make, is that this is a very exciting time for you to join if you don't want to be bothered by all the infrastructure building that's already done. So all you can do is just science. Interesting science. So it's a great time for you to join. So with this conclusion slides, I'll wrap up my talk and be open to any questions. Thank you.
Thanks, Ji-hoon. Okay, questions?
Thank you for the talk. It's really beautiful work. I have 2 questions, so I'm curious, in this process of reducing the free parameters, what principles do you have to ensure convergence to a physical result rather than convergence of codes? And relatedly, what is your view of the role of comparisons to semi-analytic or otherwise like simplified models in this framework?
Yeah, so the first question, so we had to set some metric for us to define a sort of calibration point, for example. So in the cosmological comparison that Santi led, for example, we imposed this one single constraint in that people should, each code group should provide their data sets that produces a certain range, certain reasonable stellar mass at redshift 4. So that was our constraint, and that's the reference point that people use to calibrate their stellar feedback, which is the only free parameter that we allowed each group to play with. And going back to your second question about sort of implications for semi-analytic model, I don't know, maybe Joel has any comments, Santi, or? I mean, that's something that I've always have in mind. For example, for this calibration that I just talked about, we used the semi-annealing model to give us the reference point that we needed. So we interacted with, always had a semi-annealing model in mind when we design our comparison, design our strategy, but sort of more longer term implications. We can chat.
Okay, let's thank the speaker once again. And
Thank you.